Hi everybody, my name is Emmanuel Danlig. I'm a second year student here at Wayne State. I'm just going to go through a practice problem for Navier Stokes for transport phenomena 1, taught by Professor Matthews. And so, yeah, jump right into it. This is from the winter exam 2 from 2019, so this is last year's exam. And we'll just jump right in. Okay, so the first part that they ask us to do is draw a carefully labeled cross-section. So the things that we need to include there are, first thing that's important is we assume laminar flow. We want to indicate which one has the higher angular velocity and include a sketch of the laminar velocity profile here. Okay, so let's jump right into that. So I'm going to do a top-down view here. So here's our inner cylinder and the outer cylinder. A little bit lopsided, but no worries there. So this will be our inner radius, R1, and we're going to label our outer radius as R2. Now we know that if we read the directions that the angular velocity here in the inner radius is going to be, this inner cylinder is going to be rotating at some omega 1, and then the outer radius is going to be rotating opposite direction, so this way at negative omega 2. Now we can also just really quick draw our velocity profile. So the way I like to do this is just draw a straight line here, and then following the curve of the cylinder here. So we know that at the boundary conditions, at the extreme conditions, which is R1 and R2, that the laminars or the lamina, or the layers of the liquid are going to be moving with the cylinder's rotation, so that we can put something like this here for this side. Oops. Didn't mean to do that. Do something like this here for this side, and this here for that side. So you want it to follow the curve, and obviously my drawing isn't the best, but you want it to follow the curve like this, and just indicate which way the velocity or the liquid will be moving. So I mentioned boundary conditions, and we can actually just write those down right now. That's going to be in part B here, but this will be counting for our part A, so we can now start on part B. So our boundary conditions is we know that at R, the radius is equal to R2, that the V theta will be equal to negative omega 2, as well as at R is equal to R1, V theta will equal omega 1. Another thing that is important to mention is that we know that there is no velocity in the z direction or the r direction. So we're going to say that both of those are equal to each other and they're both equal to 0. The only velocity component that we do have in the system is going to be v theta, which is also going to be a function of r. So what that means is as r is changing, as you measure at different points between the two cylinders, the velocity is going to be different, and that is outlined here by this velocity profile. So yeah, we'll keep that in mind as we move on with part B. So this says to simplify the continuity and Navier Stokes equations to obtain differential equations describing flow in this system and list the boundary conditions that could be used to solve these equations. So how I'm going to do this is I'm going to just go through one of the dimensions with you, and then I'll just tell you what we end up with the other the other dimensions. So this system is going to be, as you can see, in the directions it's made of cylinders. So that tells us that we should probably use the cylindrical coordinate system. And what that is, of course, is z direction this way. We'll have some r direction, and then obviously we're going to need some sort of angular thing here, theta. So that means that the three dimensions that we're going to want to evaluate the Navier Stokes in is r, z, and theta. So let's just look at r here. So I will not, you guys can look at your, I'm just going to verbally go through each of the terms and only write down the one that that's left over. Okay, so the first term is a density term. That's still there because the liquid has a density. The next term is dv r over dt. And there's nothing in the problem that indicates that the velocity, well, first of all, we know that the in the r direction there is no velocity, as we discussed before. So we can call that term 0 anyways, but we also know that the vr, the velocity in the r direction there is no time component in this, so we can also eliminate it on that grounds. The next term has a vr in it, so that's 0. We can cancel that out as well. The next one has v theta over r times dvr over d theta. And as we know, again, vr is equal to 0, so we're going to cancel that term out as well. The next term is vz times dvr over dz. And for the same reason, we're going to cancel that one out. The only one that might be left over is this negative v theta squared over r. Because this is not 0, it's finite. It's measurable. Okay, so on the right side of the equation here, we're going to say there is no pressure difference between the inner and outer cylinders, so we're going to call that 0. And all the rest of these have a VR in it, except for the last term, or second to last term, which is 2 over r squared times dv theta over d theta. The reason that we can cancel that out is because we know that the v theta is a function of r, not a function of theta, so that is also equal to 0. And we also know that rho gr, there is no gravity component in the r direction. The gravity component is actually in the z direction. So if you can see up here, it says that they're vertical cylinders. So we also know that that component will be 0. So what we're left with is 0 on that side, so that we know that this is also equal to 0. So in the r direction, we don't have any Navier Stokes to evaluate. The next one we're going to look at is theta. So obviously there is a rho here. So rho, but we're gonna find out that everything in here cancels out because the first term, which is dv theta over dt, doesn't change because while there is a velocity in the theta direction, it does not change with respect to time. The vr here will be the next term, which is vr times dv theta over dr. Although the dv theta over dr is a real term, vr is not, so that's a 0. That can cancel out as well. The next one has v theta changing with respect to theta, that is also 0. Next is v theta changing with respect to z, that is 0. And the next one has a vr term in it, so that's also 0. So actually we can just cancel out this density as well and just call it 0. And that's equal to 1 over r. So the first term on the right side of the equation is negative 1 over r times dp over d theta. That is also going to be 0 because the pressure doesn't change as you go around the circle. So that's 0. The next term is mu here. Mu times, mu is just viscosity, of course. So mu times dr, 1 over r times dr times r v theta. Now we keep this one because it has a v theta term and it changes with respect to r, and that lines up with what we were saying earlier. Everything else actually cancels out, though, because the v theta doesn't change with respect to theta, v theta doesn't change with respect to z, and vr is 0. There also is no gravity component in the theta direction, so as you move around this cylinder, there is no gravity. So this is all that we're left with here on the theta component. This is also going to be our main, differential equation. All right, the last direction that we're going to want to look at is the z direction. And as we cancel out all of those, what we end up being left with is this right here. 0 is equal to negative dp over dz plus rho gz. So this is just the gravity component, and we know that the gravity component is in the z direction, so this lines up that this is here. And the pressure difference, there is a pressure difference between the top and the bottom, and the reason for that is this gravity component, which is why these are the only two things left in the z direction. And this is not something we're going to need to solve either. But it is important to know that it's here. All right. So the next thing that we want to simplify is the continuity equation. So if we look at that, I'll just write it out here. So dp dt plus 1 over r d dr times rho r vr plus 1 over r d d theta times rho v theta plus d dz times rho vz is equal to 0. So this has a vz in it, that's 0. This has a vr in it, that is also 0. Pressure does not change with time, so that's 0. And we also know that v theta doesn't change with respect to theta, so that's also 0. So what we're left with in the continuity equations is 0 is equal to 0. Okay, so that's all for part B. So now if we move on to part C, which tells us to solve your differential equations to develop algebraic expressions for the shear stress, velocity profile, and the drag force on the outer cylinder. Okay, so a few tips on this one. First is that we can go through all of the math first to find the different, things for shear stress, velocity profile, and the drag force on the outer cylinder without ever solving for the constants, and then we can go back at the end to solve the constants. That's just a quick tip in case you find yourself on this exam and you find yourself running out of time. I recommend just going through all the math first, leaving in the C1 and C2, and then coming back and saying, okay, now I can solve for C1, C2, because you'll lose less points that way. Okay, so let's just get started here. So the main differential equation that we're going to be wanting to solve is here in the theta direction right here. So it's going to be 0 equals mu d dr 1 over r d dr times r v theta. Okay, so we're going to want to first separate and integrate. So 0 divided by mu is still 0, so we can cancel out that term actually. But we can separate this here. dr is equal to d dr r v theta. And then just integrate both sides like so. And what you're left with here is 0. We'll always come back, integrate to be a constant, so that's C1. And then this will be just this term here, so that's 1 over r d dr r v theta. So now we're going to want to do the same thing, separate and integrate. So we're going to move this r over to this side. C1, rc1 is equal to times dr is equal to d vr v theta vr. like that. Integrate both sides like here. It'll be r squared c1 over 2 plus some c2 is equal to v theta r. And we're going to want to isolate this v theta, so we'll just divide both sides by r. r c1 over 2 plus c2 over r is equal to v theta. All right, so this, I think, satisfies. See, does that satisfy part 1? No, that is just the velocity. That is just the velocity profile, I believe. Okay, so now we can go do shear stress. So this will be actually for part 2 right here. This is part 2. Part 1 is going to be shear stress. So we're going to look at our definition for shear stress. And this is going to be equal to negative mu. Oops, that was weird. Negative mu r d dr times v theta over r plus 1 over r dr d theta. R doesn't change with respect to theta, so we're just going to say that's 0. Excuse me, I think that is actually supposed to be dvr, but in either case, this term should be 0. Okay, so now we're just going to plug in this right here into here. So I'm going to say tau over theta is equal to negative mu times r d dr. So v theta divided by r, so just divide this whole thing by r. And then we're left with c1 over 2 plus c2 over r squared. So we integrate this again, or excuse me, derivate this, and this will be 0, and this will go down, this will become tau r theta negative mu r, and then r times negative 2 over r cubed c2. And then what we're going to be left with is tau r theta is equal to negative mu, positive mu times 2 times c2 over r squared. Okay. So that's part 1. Now we're going to move on to part 2, and then on to part 3, and then solve for our constants. So part 3, the definition of the drag force is Fd is equal to tau r theta times the surface area. And if we look at our surface area, it's just going to be the inside or the outside of the cylinder, depending on which drag force we're going to want to look at. So I'm going to say that the surface area is equal to h times 2 pi r. So we just take our tau r theta, which we found right here, and multiply it by h times 2 pi r. And what we'll be left with is some it's supposed to be a subscript. It's equal to 4 mu pi h c2 over r. All right, and now we can solve for our constants. So if we go back up to here, we found our boundary conditions earlier, stating that r is equal to r2. Then the velocity here at this edge is going to be equal to the negative this negative omega 2, and same thing at the inner. So what we're going to do is essentially take that and plug those into our v theta. So now we go back to solving for constants. And to remind us, this is our v theta right here. So R2 C1 plus C2 R. All right, so now we plug in R is equal to R2, v theta is equal to negative omega 2, R is equal to R1, v theta will be then equal to omega 1. Okay, so if we plug both of those in, the omega 1 is equal to R1 over 2 C1 plus C2 over R1, and then omega 2, negative omega 2 is equal to R2 over 2 C2, C1 plus C2 over R2. All right, so we can take these and essentially isolate the C2s, which is what I did. And that will leave us with C2 is equal to omega 1 minus R1, 2, all this times R1, and C2. And this variable equal to R2 times, negative R2 over 2 C1 minus omega 1. Set these equal to each other. Essentially, we just simplify out, substitute, and eliminate. And what we're left with is C1 will equal R1 omega 1 plus R2 omega 2 all over some R1 squared over 2 plus R2 squared over 2. And then C2, once you plug this mess back into here, will get you R1 times omega 1 minus R1 over 2. And R1 squared plus R2 squared over 2. And this will be, of course, C2. All right, and those are the constants. Professor Matthews is usually pretty lenient when it comes to partial grading, so you can leave these in this form. You don't actually have to rewrite any of these if he sees that you've solved for your constants already here at the bottom, like so. Okay, and for the last part, it's under conditions of opposite rotation. There will be a location where the fluid velocity is 0. Find this location of 0 velocities in terms of angular velocities and system dimensions. All right. So, angular velocity is, so we essentially want to find the r where the v theta is equal to 0. This is for part D. So we can go back actually to our simplified form of v theta, and we'll just put v theta r 0 is equal to c1 rc1 over 2 plus 1 over rc2. So we can isolate r, we can actually isolate the r value here. So what we can do for that is just do negative rc1 over 2 plus 1 is equal to over rc2. Multiply that by r, divide this by c1, and what we're left with is r squared equal to 2 c2 over negative c1. And then take the square root of both sides, and r is equal to 2c2 over negative c1. And I just left my answer like this, and then you can just put where C1 is equal to the mess that we found up here, and so is C2. So that's equal to whatever those are. And he seemed to take that as an answer. All right, that should be it. Thank you guys for watching. Hopefully, good luck on your Navier Stokes problems. All right, bye.